As we write functions, sometimes we run into anomalies that our code can't normally handle. As programmers, we need to decide what to do when those anomalies arise. Let's take a specific example. Say we wanted to write a function to calculate the nth element of a list. The function should accept a list of values. The list doesn't need to be of any specific element type, so the polymorphic type alpha list works here. The function will then accept an integer n, and the function should return a value of type alpha representing the element of the list at index n, where index 0 is the first element in the list, index 1 is the second element in the list, and so on. How would we implement the function? We could match the list to a head and a tail. If n equals 0, then we want the first element of the list, which is just the head. Otherwise, we can recursively call the nth function on the tail of the list and the index n-1. This works because the nth index in the full list is the same as the n-first index in the tail of the list. Once we've defined the nth function, we could use it. We could get the element at index 0 in a list, or the element at index 2 in a list, for example. But one thing you might notice, and one thing we'll be warned about, is that this pattern match is not exhaustive. It's possible that a list won't match anything, and in particular, that would be the case for the empty list, which doesn't have a head and a tail. When might this function ever run into the empty list case? Well, imagine we tried to call the nth function on the list 1, 2, 3, and tried to access the value at index 5. The function will recursively call itself, each time on a 1 shorter list, and each time on a 1 smaller index. But since the list has only 3 elements, we'll reach the empty list before we reach index 0. This is an anomalous condition, and it's one that we'll need to find an appropriate way to handle. Let's start by looking at a bad way to try to handle this anomaly. One way to approach the problem would be to use some value that represents an error. We might define a value to be an error value, say the number -1. And then in our nth function, we could return that error value if we were to ever reach the empty list case. In some sense, this does handle the anomalous condition. If we wanted to detect if the nth function wasn't able to determine the nth element of the list, we could check to see if the return value is equal to the error value. But there are a few problems with this approach. The first problem has to do with the type of the function. The original version of the nth function we wrote has type alpha list to int to alpha, a polymorphic type that represents a function that accepts a list of any type, then accepts an integer index in the list, and then returns a value of the same type as the elements in the original list. But now, with the version of the function with an error value, the function has type int list to int to int. It's no longer polymorphic. It doesn't work with any list, it only works with integer lists. And that's because our error value is an integer, so the function as a whole must return an integer. The second problem with this approach is that it manifests in-band signaling. By that, we mean that we're using an otherwise valid value to indicate some kind of special information, like the presence of an error. If we were to run the nth function and get back the value -1, it wouldn't be clear either to us or to our program whether that means there was an error or whether the value -1 is actually the value that's at the index we were interested in. So this in-band signaling isn't the best design. We lose polymorphism, and we might confuse a valid value for an error value. Instead, let's look at 2 better approaches to handling anomalous conditions. The first approach is to use what's known as an option type. The basic idea of an option type is that we want a type that allows us to represent the absence of a value. An option type is a kind of structured data type, and it has 2 value constructors. None, which indicates the absence of a value, and sum, which is a value constructor that takes an argument for a value we want to represent. Let's take a specific type. Int is an atomic type we're familiar with by now. It's the type used for integers. -1, 0, 1, and 2 are all examples of integer values. But there's no value of type int that could represent the absence of an integer, a value that we could use in the event of an anomaly. So instead of using the type int, we could use the type int option. Int option is a type whose values might represent some int, but also might represent the absence of an int. To represent an int value, we could use the sum value constructor. So sum -1, sum 0, sum 1, and sum 2 are all valid values of type int option. And to represent the absence of an integer, none is also a value of type int option. Using the int option type, we now have the ability to express either an integer or none, which we can use in anomalous cases. We can construct option types from any other type too. We could have float option values, int cross int option values, or bool list option values, for example. In each case, we use the sum and none value constructors to construct these optional values. This gives us a possible way to rewrite the nth function. We could write a function nth opt that accepts an alpha list and an index in the list, and returns not an alpha value, but an alpha option, a value that might contain an alpha value, but might also be none if there is no value at that index. Then our function can return none if there is no value at the index, or some value if we found a value at that index. It's important to remember that types and their corresponding option types are different types, so they can't generally be used in the same ways. For example, if we had an int value and we wanted to add 1 to it, then we would get a new int value that's 1 larger. But if we had an int option value and tried to add 1 to it, we'd get an error. To use the plus operator, we need an int, but we have an int option instead. This error is to be expected. We can't just treat an int option like an int because it's not always going to represent a particular integer. It might be none, and what does it mean to add 1 to none? When we try to use option type values, we often need to be explicit about what to do when the value is none and when the value is some value. To do that, we can again use pattern matching to decompose the option type value and get access to the value that may be stored within it. Say, for example, we wanted to write a function to check if an int option value was a positive integer. We could pattern match the argument. If the argument is none, then it doesn't represent a positive integer, so we could return false here. Otherwise, the argument is some v, where v is a name we've given to some int value. And since v is an int, we can use it like an int. We can compare to see if it's greater than 0 to determine if the number is positive. Admittedly, having to pattern match option values to extract the values within them does have the potential to make our code more complex and less elegant. But if we're working with functions that regularly result in anomalous conditions, option types are often well suited. We want to make sure callers of those functions know that anomalous conditions are to be expected and should be explicitly handled appropriately. But when anomalous conditions are rare in a function, and it's not something you'd expect the caller of the function to handle, we have a second alternate approach for dealing with anomalous conditions too. Instead of using an option type to mark the return value as an anomaly, we can change the flow of control of the program by raising an exception. When an exception is raised by our program, execution of the function stops. And when execution of the function stops, it can't return a value. So we generally use exceptions in cases where a function doesn't have an appropriate value to return. So when a function raises an exception because it can't return a value, the function that called it also can't return a value, so its execution must stop, which means the function that called it can't return a value and must stop execution, and so forth, halting execution of our entire program. Here's a version of the nth function that raises an exception, in this case the exit exception that's built into OCaml, in the event that there is no value at the index. Otherwise, it returns the value at the index. Notice this function returns alpha and not alpha option. We're returning the nth value itself. When there is no nth value, we don't return none. We instead raise an exception to stop execution of the function altogether. And notice that to raise an exception, we use the raise keyword followed by an exception value. If we try to use this nth function on an index that's out of bounds, we'll see that execution stops and we see the exception. Exit is a general purpose built-in exception in OCaml, But there are other exceptions we could use to be a bit more specific about what specifically went wrong. For example, the invalid argument value constructor takes a string and constructs an exception that's used to indicate that an argument to a function is inappropriate. And the failure value constructor also takes a string and constructs an exception that's used to indicate situations where the function isn't well defined. The string we provide to these value constructors is shown when the exception is raised, acting as an explanation for what went wrong. So we could improve the design of our nth function by using these more specific exception values rather than the general purpose exit exception. We might raise an invalid argument exception if the argument is negative, since a negative value is an inappropriate value for an index in a list, and we might raise a failure exception if we run into the empty list case, since that means the index was too large and the element at that index isn't well defined. By default, when an exception is raised, it stops execution of the function, its color, and so forth, stopping execution of our whole program. But sometimes we might actually want to handle the exception ourselves, rather than let them propagate to the top level of our program and stop execution. To do that, we can use the try with construct, which looks like this. We try to evaluate an expression. If it's evaluated successfully to a value, this whole expression evaluates to that value. But if the evaluation of the expression raises an exception, then we match the exception. If one of the branches of the match expression fits the exception, then we evaluate its corresponding expression to determine what this whole expression should evaluate to. Say, for example, we wanted to write a function to determine if the nth element of a list of integers is a positive integer. To get the nth element of the list, we could just use the nth function we've already defined, and then we could check to see if it's positive. But we know that nth might raise an exception, like failure or invalid argument. So let's handle that. Instead of letting exceptions propagate to the top level, let's wrap the exception in a try construct. We're going to try to compute the nth element of the list and check if it's greater than 0. But if evaluating that expression raises an exception, we'll handle those cases. If nth raises either a failure exception or an invalid argument exception, we might decide to just return false here, for example. Options and exceptions are both valuable ways of handling anomalous conditions. They differ in some key ways. Options are explicit. The type of the value indicates that it might be an anomaly, and the compiler will therefore enforce that we handle those anomalies. Exceptions are implicit. The compiler won't enforce that we handle the anomalies, but our code might be more concise as a result. In general, we'll often use options if the anomaly is a frequent or standard part of the computation, since we'll want to explicitly handle those frequent anomalies. Options are also common when the anomaly is localized to a small part of the code, since we can add option handling just in that region of the code. Exceptions, meanwhile, are often useful in rare occurrences, where we may not want the added complexity of always ensuring anomalies are explicitly handled. This is especially true if the anomaly is ubiquitous and could occur anywhere in the code. Writing code to explicitly handle option values everywhere can be cumbersome, so it can make sense to use exceptions instead. Whichever we use, options and exceptions both give us ways of dealing with anomalous conditions when they arise in our code, giving us design choices for how we want to cleanly and appropriately handle anomalies in our programs.